All right, today we're going to do as many problems related to integrals as we can from chapter 5. Just do a nice, good sampling of various kinds of problems. One kind of problem that I want to emphasize to start with is a problem where you've got a grid, essentially some graph paper, and the graph you're interested in is graphed on the graph paper. It's number 22 here, right there. This figure gives you your velocity during a trip starting from home. Positive velocities take you away from home, and negative velocities take you toward home. Notice the horizontal axis is right here. It's not bold-faced, but that is the horizontal axis. Maybe I should try tracing this to some degree here at least. Probably hard for you to see. It's actually kind of hard for me to see here. You can see it a little bit here. Something about like this. Something about like that. Okay, it's not perfect. T time is in hours. V, the velocity, is in kilometers per hour. Excuse me. And again, it says positive velocities take you away from home. So in the first 3 hours, the velocity is positive. That means you're going away from home. Away from home is the positive direction. Excuse me. Whichever direction that happens to be, whether it's east, west, north, south, it doesn't matter. It actually even doesn't matter if the road curves. They're just velocities that are taking you away from home, and negative velocities are taking you back toward home between time 3 and time 5. Question is, where are you at the end of the 5 hours? When are you farthest from home, and how far away are you at this time? The key principle is that when you've got a velocity function, if v equals f of t is your velocity at time t, then over any interval where you integrate the velocity, you're going to get your change in position. That's the key principle. This is the change in position, which could be positive or negative. Your change in position, if it's positive, that means you ended up further away from home than where you started. If it's negative, it means you ended up closer to home than where you started. And we're not saying where you started. We're not saying you started at home. I guess it does say it started from home, but in general, it doesn't have to. This is from t equals a to t equals b. Also called the displacement. Displacement and change in position mean the same thing. From t equals a to t equals b. Over whatever interval that we're talking about here. A to b is whatever subinterval here that we happen to be focused on. Think about it intuitively and also try to get numerical answers. For the first 3 hours, the velocity is positive, so that means you are traveling away from home that entire time. From time 3 to time 5, the velocity is negative, so at time 3, you turned around and you went back toward home. So it should make some intuitive sense then that at least where you're farthest from home should be at t equals 3. And your farthest distance, so you're farthest from home, at time t equals 3 hours. That's one answer to one of the questions. I explained it to you verbally. The reason is for the first 3 hours, you're moving away from home because the velocity is positive. And again, from time 3 to time 5, you're moving back toward home. So you have to be furthest away at time 3. How far are you at that time? I guess we're taking these questions out of order. It's the integral. Distance from home, if we do start at home, at t equals 3 is going to be the integral of this velocity function from time 0 to time 3. The distance from home when you travel in the positive direction will be the same as your change in position. If you start at home, same as the displacement. We don't have a formula for F, so we can't integrate this with the fundamental theorem of calculus. Instead, we need to estimate the area under the curve. And from time 0 to time 3, we want to estimate this area. There's a couple ways you could do it. You could do a left-hand sum and a right-hand sum and average them, perhaps. You could also count boxes and figure out the area of each box. Let's do it both ways. Okay, and this is something you should be able to do for the final, or for the exam 3. Again, we're not going to have a final this semester. How much area does each box have? Area of a box, a rectangle, is base times height. For each one of these, the base is 1 and the height is 10. Think about the units. 1 hour for the base times 10 kilometers per hour for the height. The area of each box can be thought of as 1 hour times 10 kilometers per hour. And go ahead and use those units, even though those are not units of area. You can cancel the hours. The answer represents 10 kilometers. Each box has an area whose units we're going to write as kilometers, even though that's not units of area, because of the way the axes are labeled. This one being hours, this one's being kilometers per hour. Multiply those, the hours cancel. Each box represents 10 kilometers of distance. Now all you have to do is just count boxes. Whole boxes and partial boxes. 1, 2, 3, 4, 5, 6 whole boxes. If I combine, say, watch where I'm pointing here, this one with this one, that partial box with this partial box, that's pretty close to a whole box. That would be 7 boxes. If I combine, say, this piece with that piece up there, this almost triangle right there, that's another combination of partial box that approximately equals a whole box. So we'd be up to 8 boxes. The only thing we're missing is this part right there, which is almost a whole box. So we're very close to 9 total boxes. Watch my pen again. 1, 2, 3, 4, 5, 6 whole boxes there. 7 when you combine these two. 8 when you combine these two. Close to 9 when you add in this partial box right there. Close enough that I'm just going to go ahead and say approximately 9. This is approximately 9 boxes at 10 kilometers area. I'm going to go ahead and put per box here, even though I didn't put it down there. I guess I could have done this per box in those spots as well. So this gives 90 kilometers. At time 3 hours, you're about 90 kilometers from home, and that's as far as you get. Does that make sense? Would we get the same thing if we did left and right hand sums and say average them? Probably not, but hopefully it's not too far off. Let's try a left-hand sum and a right-hand sum. Focused on the interval from 0 to 3, broken up into 3 pieces, subintervals of width delta t equals 1. A left-hand sum would take f of t0 times delta t plus f of t1 times delta t plus f of t2 times delta t, where t0 would be 0, the left endpoint of the first interval, t1 would be 1, the left endpoint of the second interval, t2 would be 2, the left endpoint of the third subinterval. And again, delta t in each case would be 1. You can estimate these values. Let me go ahead and plug the numbers in here. This is f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1. F of 0, looking at the graph, looks like it's 30. F of 1 is close to 40, a little bit less. Let's go ahead and say, is that close enough to 39 to say 39? Okay, I'll go ahead and say 39. Maybe closer to 38. I'd be okay with either answer. Then f of 2, how high does the graph go there? It looks like it's 32, 33, something like that. I'll say 33. Add those numbers up. You're going to get 102 kilometers for your left-hand sum approximation. That makes sense? I'm not wanting to draw in my book because I don't want to mess up my book, but the first rectangle would be essentially these 3 boxes put together. The second rectangle would be these 4, maybe a little lower than the top there because it's up to 39. And the third rectangle would be approximately this high right here. That value right there where I'm pointing is about a velocity of 33. A right-hand sum is going to look at the right endpoint of each interval and use that to plug into the function to get the height of the approximating rectangle. So the first term is not f of t0 times delta t, it's f of t1 times delta t. Second term is f of t2 times delta t. Third term is f of t3 times delta t. That's f of 1 times 1 plus f of 2 times 1 plus f of 3 times 1. Those first 2 terms are the same as what we got there and there. 39 times 1 plus 33 times 1. F of 3, though, is different. In fact, it's 0. F of 3 is 0. There's no rectangle for the right-hand sum on this interval. It's a rectangle with a height of 0. That's 0 times 1. So this approximation gives 72 kilometers. Probably the best approximation we can do based on this approach then is to now just average these 2 numbers. LHS plus RHS divided by 2. 102 plus 72 divided by 2 is 174 divided by 2, and that's going to be 87 kilometers. Yeah, not too far from the 90 kilometers we guessed by counting boxes. Both of them are decently close to each other. They'd both be okay answers. Question? Say it again. You could. I'd also be okay with a number that's relatively close. By the way, when you average the left and right-hand sums, that does have a name. It's called the Trapezoid Rule. And it is related to areas of trapezoids, but I don't want to get into details. So either approach is okay. You should be able to do either approach if I told you use one approach or the other. If I don't tell you which approach to use, you're free to use either approach. Where are you at the end of 5 hours? We didn't answer that question. What's your change in position from t equals 0 to t equals 5. That's going to be the integral from 0 to 5. We already did the integral from 0 to 3. We need to add on the integral from 3 to 5. That's a property of integrals. We already did this one. Let's go ahead and say this part is approximately, I'll go ahead and use the 87. That's approximately 87, say. But now I also need to add on the integral from 3 to 5. But careful, that integral is going to be negative because the graph goes below the axis. You got to count boxes in their areas, but they contribute negatively to the integral because you're traveling toward home, and that's causing your change in position to get smaller than 87. How many boxes are there that are below the axis? Well, there's one whole box right there. If you combine this partial box and say this partial box, that's a bit more than another partial box. Maybe it's about up to 2.25 boxes, then add on this one, and that's a small amount. I don't know, somewhere around the ballpark of 2.3, 2.4 boxes below the axis or below the axis and above the curve when the curve is below the axis here. Here's the t-axis. Let's just pretend it's 2.4. 2.4 boxes. But now multiply that, not times 10 kilometers per box, but negative 10 kilometers per box. Because they contribute negatively toward the integral, because the graph is below the axis. So that's about negative 24 kilometers is what this represents. This is approximately minus 24 kilometers if I use that approximation of 2.4 boxes. I mean, if you guessed anywhere between 2.2 and say 2.6 boxes or maybe 2.5 boxes, I'd be okay with it. The final answer then is 87 minus 24. That's going to be 63 kilometers for the final answer. As a rough approximation. So the integral from 0 to 3 was about 87. The integral from 3 to 5 was about negative 24. The combined integral from 0 to 5 is the sum of these two, though one of them is negative. 87 plus negative 24 is the same as 87 minus 24 is 63. Can I clarify anything? We good with this? Pretty important kind of problem to be able to do. Section 5.2 has more problems with graphs on graph paper, so to speak. For example, number 16 here. Estimate the integral from negative 10 to 15 of this function. It's above the horizontal axis, so that integral is just going to be the area under the graph. From negative 10 to 15, note that this graph starts at negative 11 or so. So ignore the first little part of it. And it goes past 15. 15 is right there. It goes past 15. So you got to focus on the part that's above negative 10 to 15. I could count boxes. Let's just do a real rough approximation by counting boxes. 1, 2, 3, 4, 5 whole boxes there in the first row. 6, 7, 8, 9, close to 10 whole boxes there. If I combine these two, that probably is up to 10 whole boxes. That's close enough maybe to count it as 11 whole boxes. Combine these two to get 12. This is essentially 13. And say combine these three things to get 14. Approximately 14 whole boxes. What's the area per box? The base is, careful, 5, right? And the height is 5. 5 squared units of area. Now, they don't give you units for the variables themselves, so let's just say square length units per box. The boxes cancel. You're left with 14 times 25. And 14 times 25 is going to be, I think, 350. 350 length squared. Now, probably you don't even need to bother with the units here, because they don't give you a context. There's no clear application. You can just say the answer is 350. This one goes both above and below the axis. You got to be careful. When it's above the axis, you count the area under the graph positively toward the integral. When it's below the axis, you count the area above the graph and below the axis as contributing negatively to the integral. Very, very fundamental things to do. Sometimes you're just told, hey, this has area 13 and this has area 2 here. Let's do this one, number 29. This was 5.2, number 16. Part A says find the integral from a to b of f of x. There's A, there's B. The graph is above the axis. That area of 13, contributes positively to the integral. In fact, the integral therefore must equal 13. B, the integral goes from B to C. B is right there, C is right there. The area is labeled as positive 2, but the integral is negative 2. It's the opposite of the area when the graph is below the axis. You can label the area itself with a positive number, but realize the integral itself must then be negative. The integral from A to C will be 13 minus 2, will be 11. If we want to write this out in a formal way that uses properties of integrals, you can break this integral into two pieces. First, an integral from A to B, and then an integral from B to C. It's not that you have to do this, but it's worth doing to emphasize the abstract property in your mind. And this is then going to be 13 plus negative 2. 13 minus 2 is 11. In D, you're asked to integrate not the function itself, but the absolute value of the function. Here you need to understand how to draw the graph of the absolute value of a function if you're given the graph of the function. Whenever the graph is above the axis, the graph just stays the same. So this part of the graph is the same. When the graph of f goes below the axis, where the outputs are negative, you have to take their absolute values. So you need to essentially flip this little piece of the graph back above the axis like this. But since it's a reflection across that axis, its area is going to be the same. The area above the curve when it's below the axis is going to be equal to the area under the curve when we flip it. So this is going to be 13 plus 2, not 13 minus 2. That'll be 15. Does that make sense? We're using the area interpretation, or more precisely what's called the signed area interpretation of the integral. Question? Yeah, if this is a velocity, the integral, which would be 13 minus 2 or 11, would be the change in position. Yes. However, when you integrate its absolute value, it does give you the total distance traveled. Total distance traveled is actually 15. You're moving, say, away from home from time A to time B. If home is right here, say you start at home, by the time you get to time B, this distance right there is 13, because this area is 13, and the area will represent the change in position. You turn around and go back toward home, you end up 11 units of distance from home by time C. However, you did travel a distance of 15 units. You went from 0 to 13, then back another 2. So integrating the absolute value still has meaning. Whereas the integral of the function itself, the velocity function itself, is the change in position. The integral of the absolute value of the velocity, which is the speed, is the total distance traveled, 15. Let's do a fundamental theorem of calculus problem. I assigned a few of these already. Let's try 14 here. These problems are phrased in kind of a strange way. In 14, you're told capital F of t is tangent of t. A is 0, B is pi. And you're told to write the integral, not of capital F, but little f. They don't say it, but it's understood if we're going to do that, little f must be the derivative of capital F. Because that's the way we're going to be able to use the fundamental theorem of calculus. So little f of t, the function I'm really integrating, is the derivative of capital F, and the derivative of a tangent is secant squared. So now, to write the integral means I'm really going to write the integral from 0 to pi, not of tangent, but of secant squared. Of the little f, not the big F. The fundamental theorem of calculus says this equals capital F of pi minus capital F of 0. That's the fundamental theorem of calculus right there. The integral of little f, which is the derivative of big F, is a change in the value of big F, where big F is tangent. So this becomes tangent of pi minus tangent of 0. And actually, I'm realizing the book, in doing this problem, I think the authors weren't thinking very carefully. Because the secant function actually has a vertical asymptote between 0 and pi. Let me change the problem. Glad I didn't assign this problem. let me change this pi to be pi over 4. All those pi's get changed to pi over 4. Tangent of pi over 4 is actually 1, and tangent of 0 is 0. The answer is 1 here if I change it to pi over 4. The author of the textbook wasn't thinking very carefully in doing number 14 and writing it that way. Why? The graph of secant squared t goes from 0 to pi has a vertical asymptote. And because of that, the integral from 0 to pi actually doesn't make any sense. We might be able to make sense out of it if we do something called improper integrals, but that's a calculus 2 subject, and it's not even clear to me that it's going to make any sense at all. If we just go from 0 to pi over 4, then the graph does not have a vertical asymptote. Looks like that. That's the graph of secant squared. And we've just said the area under this graph we've just found to equal 1. Let's check it with Mathematica. Use your writing assistant here. Press the integral button. Go from 0 to pi over 4. You can make a pi by doing escape, p escape. Makes a pi. Escape, p escape. I just integrated secant of t, quantity squared, dt. This should equal 1. Yep. Because of the fundamental theorem of calculus. Because the fundamental theorem of calculus says that when integrating the derivative of something, find an antiderivative of that something and find capital F of b minus capital F of a, where in this case a is 0 and b is pi over 4. The FTC essentially says that this kind of integral can be computed by doing capital F of b minus capital F of a if capital F prime of t equals little f of t for all t in the interval from a to b. If little f has an antiderivative, call it capital F, we can find this integral by doing this difference. This is, like I said on Monday, astonishing. You don't have the experience to appreciate how astonishing this is. Actually, I mean, that's true for a lot of things in math. Did you know the Pythagorean theorem is an astonishing theorem? Right triangle, A, B, C. The fact that c squared equals a squared plus b squared, why in the world should that be true? It's astonishing. Amazing. We just don't appreciate it because we're so used to it. But the Pythagorean theorem really is an amazing fact. There's a reason it's so famous. Partially because it's really useful, partially because it's really amazing. Who would ever expect that would be true if you weren't told by your teacher? Same kind of thing with the fundamental theorem of calculus. Who would ever expect you could find an area under a graph by plugging numbers in and subtracting into an antiderivative? Who would ever know such a thing unless your teacher just tells you? Seems like magic. There's no intuition at the moment at least, as to why this should be true. But it is true. And that was Newton's and Leibniz's genius, was to realize that the fundamental theorem of calculus is true, to essentially describe it and use it. That was their stroke of genius. Other people before Newton and Leibniz had done things calculus related. For example, somebody named Fermat had figured out how to find tangents to curves and critical points, really. That came before Newton and Leibniz. What Newton and Leibniz did was they connected integrals to derivatives. And that's what the 3 blue 1 brown video is about. And I'm going to do another one here that you should watch before Friday, is connecting areas to slopes. Somehow they're connected to each other. This integral gives you the area. This function, capital F, that you evaluate like this, has slopes equal to the original function you're integrating. Very mysterious. But you do enough examples, you start to believe it. Another example here. Maybe I'll try an example that's not so, it's not so clear what the answer should be. What if we integrate, say, the natural log function? Oh, how about from 1 to, maybe I should use the power of e here, e squared. According to the fundamental theorem of calculus, if this is my little f of x, if I can find a capital F whose derivative equals little f, then I can just do capital F of e squared minus capital F of 1. Where capital F prime of x equals natural log of x for all x in the interval from 1 to e squared. How do you find capital F here? The answer is not 1 over x. 1 over x is the derivative of natural log of x. I'm after a function whose derivative is natural log of x. Okay, you can do it by trial and error. That's one way to come up with a formula for capital F. We can use Mathematica to find it as well. In fact, we can do an indefinite integral. This button here. And remember that natural log in Mathematica is actually log. If I do an indefinite integral like this, this is going to give me an antiderivative. Negative x plus x natural log of x plus c. Mathematica doesn't put the c. If Mathematica was doing an integration gateway in Calculus 2, Mathematica would fail because it's forgetting the plus c. However, when we do these integrals, we don't need to worry about the plus c because it would cancel anyway when we do the subtraction. So when you do definite integrals, you can always just assume c is 0. And again, the answer here is, well, x natural log of x minus x. Capital F of x is x natural log of x minus x. Let's check that by differentiation. Capital F prime here, I need the product rule, right? I got a product of two functions there. X times natural log of x, the derivative of the first function is 1 times the second function, plus the first function, x times the derivative of natural log of x is 1 over x, minus the derivative of x is minus 1. Hey, and that's a positive 1, those cancel. And 1 times natural log of x is natural log of x. Indeed, Mathematica is correct. This function is an antiderivative of ln of x. So now go ahead and use it. Actually, use this one. So I'm going to get e squared natural log of e squared minus e squared. That's capital F of e squared. Right? I'm plugging into this. Subtract what I get when I plug in x equals 1. 1 times natural log of 1 minus 1. Careful about minus signs. Natural log of e squared equals 2. 2e squared minus e squared is e squared. Natural log of 1 is 0. 2 minuses make a plus. The answer is e squared plus 1. Check it. Do a definite integral instead of an indefinite one. From 1 to e squared, you got to do capital E squared to get the number e. Log of x. This should be e squared plus 1. Yep, 1 plus e squared. Mathematica spits back the e as a fancy looking e. LOG means ln actually. Yes, in mathematics. Tracking with me here? What about, say, something like, oh, how about the integral from 0 to, oh, I don't know, square root of pi over 2 sine of x squared. This is my little f of x. According to the fundamental theorem of calculus, that's going to be capital F of square root of pi over 2 minus capital F of 0, where capital F prime of x always equals little f of x for all x in the interval from 0 to square root of pi over 2. However, there's a problem here. You could try finding capital F all day. In fact, you could keep trying to find capital F the rest of your life and you would never succeed. What? Well, unless you know how to cheat. I actually know how to cheat. Well, one way to do that is with Mathematica. When I say cheat, I don't literally mean cheat, but it just feels like cheating. Mathematica, what's the indefinite integral of sine of x squared? FresnelS. What? FresnelS? What in the world is that? It's a new function, your very own function you've never heard of before. Hey, you heard of it today. It's a Fresnel sine function, it's called. What? There are plenty, in fact, infinitely many functions you've never heard of before. How many of them actually have names? Probably thousands. There are thousands of functions that have names that you've never heard of before. FresnelS is one of them. What is it, though? Well, it's a function that you can actually graph. You know, before you took trigonometry, you'd never heard of sine, cosine, and tangent. Before you took calculus, you've never heard of FresnelS. Pretty graph, huh? Look at that. What's it good for? All various things in science. It comes up. I'm pretty sure it comes up in optics, if you need to take optics sometime. Interesting graph. So does that mean that integral can't be done? The integral can be done. It's just that the answer depends on FresnelS. Though maybe it can be simplified. Okay, involving FresnelS of 1. The answer is about 0.549276. The fundamental theorem of calculus is still true. This is still true. It's just not very helpful because the answer involves FresnelS. So because of that, in doing things like this, you either need technology or you need to approximate the answer in some way, like with the left-hand sum, a right-hand sum, and maybe the average of the two. Sometimes you have to use those Riemann sums and not even bother with limits. You're just trying to approximate the integral. Very, very fundamental stuff that I'm telling you here. But it's the kind of stuff that's easy to forget in, say, 20 minutes from now. Work at rethinking about your notes. Look at your notes and rethink about this stuff. It's worthwhile to get it in your mind and try to make it stick there. To end class today, we'll look at section 5.4. 5.4 is got a bunch of properties of integrals, a bunch of theorems. Let's just summarize the theorems. And you should be able to apply these in problems that are conceptual in nature. Properties of integrals are really important, just like properties of derivatives are. This property here says if you switch around the limits of integration, notice this integral has a lower limit of a and an upper limit of b, but this integral has them switched around. Then you need to put a minus sign in front of one of those integrals. It doesn't matter which one. I could have put the minus over there. When you switch around limits of integration, you need to compensate, so to speak, by putting a negative sign in. That's the first property. The second property right here, I've actually already used today. It's easiest to think about if the graph is above the axis. If this is A here, B here, and C here, the integral from A to C is the total area under the curve. And you can, excuse me, that's the integral from A to B. Let's change this labeling. Let's make that a C and this a B. The integral from A to B is the total area under the curve. And the fact that it equals the sum of these two integrals means you can break that area up into two pieces. The area under the graph from A to C, this piece right here, plus the area under the graph from C to B, this piece right here, equals the total area under the graph, is what this says. Though this property actually works even if the graph goes below the axis, and even if the integrals are negative, it still works. It's pretty handy. These are pretty handy properties sometimes. I'll hint at reasons why on Friday. Next property, page 300, is this theorem. This is a linearity theorem. You remember I said the derivative operator is linear? ddx. ddx of f of x plus g of x. The derivative of a sum is the sum of the derivatives. It's f prime plus g prime. Integrals are linear as well. The integral, take the plus sign here. Excuse me. The integral of f of x plus g of x is the integral of f plus the integral of g. If I take the minus sign, I could say the integral of f minus g is the integral of f minus the integral of g. It's kind of like a distributive property for the integral sign, but not literally. Moreover, if you've got the integral of a constant times a function, the constant can be brought out in front. Derivatives have very similar properties. For derivatives, I can say ddx of f of x plus or minus g of x is f prime of x plus or minus g prime of x. And I can also say the derivative with respect to x of a constant times f of x is that constant times the derivative of the function. That's linearity for derivatives. These linearity properties for integrals are pretty much very similar kind of theme. It's saying something different, but it's a similar kind of theme. Here the ddx goes through the parentheses and becomes primes if you prefer. Same kind of thing here. Here the integral sign goes through the parentheses and the constant factors out in front. Very fundamental properties. This property says the area between the graphs of two functions, f and g, where the graph of f is above the graph of g, is the integral of their difference. I need to find the area between two graphs. This property says if f is an even function like this one, its graph has symmetry about the vertical axis, then the integral from negative a to a, notice these are opposite signs here, negative a and a, is 2 times the integral from 0 to a. In other words, the area under the graph from negative a to a is the same as double the area under this piece from 0 to a. That's got to happen by the symmetry. You can see it in the picture. On the other hand, if g is an odd function, like this, it's got origin symmetry. The integral from negative a to a is going to be 0 because this area contributes positively to the integral and this one contributes negatively. And they have the same area because I'm going from negative a to a. Therefore, they have to cancel each other out and the integral is 0. These are very useful properties in an advanced topic called Fourier series. And Fourier series is foundational to everything in engineering, especially to electrical engineering and signal processing. These integrals are essential for electronic components working, okay? People figuring out integrals based on these facts. I'm going to skip this one for the moment and end class by looking at this one here. This is not a theorem to derive. It's really a definition. It's a way to define what the average value of a function is. How is it defined? Do the integral of the function and divide by b minus a, the length of the interval. That is the definition. It's not, again, this is not something to prove. It's the definition of what average value of a function means. And it is related to what you would intuitively think of as like the average height of a graph. If the graph of f looks like this, over the interval from a to b, the average value of f is essentially an average height, you could say. What's the average height of this graph? It's somewhere between the extremes, the low values here and the high values up here. Maybe somewhere right around here is the average height. Let me call it f sub AVE for the average value. The definition of the average value is chosen in such a way that the area of this rectangle is the same as the area under the purple curve. The average value of f of x is an average height of the graph, again, so that the area of the red rectangle, whose base goes from a to b and whose height is the average value of f, is the same as the area under the graph of f, the same as the integral. That's way more important than you might imagine. It's especially important in multivariable calculus, helping you understand the subject better. It's a key idea that generalizes to higher dimensions and can help you understand some higher dimensional ideas a lot better than you would otherwise. Okay. There will be a quiz on Friday. That quiz will cover through these conceptual topics that we talked about today. It'll mostly be about integrals. Okay. See you on Friday.